We did the impossible. We sent humans to the moon, walked on its surface, and brought them safely back home. And we didn't just do it once, we did it 6 times. So naturally, you might think that going to Mars is just the next step, right? Same plan, just a bit farther, a little more fuel, a slightly longer trip, and a few more rations. Fundamentally, it seems like the same problem. After all, we solved the hard part already. The moon was the nut, and we cracked it. Mars, just another stop down the same road. But that idea is dangerously wrong. The truth is, Mars is an entirely different challenge, and I'm going to show you exactly why. This is one of those rare moments where common sense doesn't just fail, it pushes you straight off a cliff. Because the moon and Mars are not the same problem at different scales. They are fundamentally different, and the difference isn't something you can fix by packing a few extra sandwiches or building a slightly bigger rocket. It's mathematical. It lives in a single, simple-looking equation, and that equation is merciless. Let's break it down, step by step. By the time we're done, you'll understand something that took engineers decades to fully grasp. Getting to Mars is hard. Landing on Mars, that's really hard. But leaving Mars and coming back home, that is a completely different level of hard. The kind of hard where nature itself seems to say no. And you have to figure out if it really means it. Before we go further, let's make sure we're all on the same page about rockets. Because if you don't understand this, nothing else makes sense. A rocket works by throwing stuff out the back. That's it. That is the whole secret. You expel mass in one direction. And by Newton's third law, the rocket moves in the other. Every rocket that has ever flown, from the tiniest model to the Saturn V, works on this simple principle. You burn fuel, heat it up, blast it out a nozzle at tremendous speed, and the rocket moves the opposite way. Simple, right? But here's the catch, and it's a brutal one. The fuel you will burn later, you have to carry it now. And carrying it now makes the rocket heavier, which means you need even more fuel to accelerate all that fuel, which makes the rocket heavier still, which means you need even more fuel to carry that fuel, too. See the spiral? It's a vicious, unforgiving loop. This is captured perfectly by an equation first derived by a Russian schoolteacher, Konstantin Tsiolkovsky, back in 1903, the same year the Wright brothers flew at Kitty Hawk. In plain words, it says this: the change in velocity you can achieve, your delta V, equals the exhaust velocity of your engine multiplied by the natural logarithm of the ratio of your full mass to your empty mass. Delta V equals exhaust velocity times the log of the mass ratio. That's it. One line, one equation, one unforgiving truth. Now, if logarithms and exponentials make your head spin, don't worry. This is where people get tripped up. They assume, if I need twice the speed, I just need twice the fuel. Wrong. No, you need far more than twice the fuel. The relationship is exponential, not linear. If you rearrange the equation to ask, how much fuel do I need for a given speed, the answer is a brutal jump in requirements, not a gentle increase. For example, a chemical rocket engine that throws exhaust at 3 kilometers per second might need a mass ratio of about 2.7 to achieve a delta V of 3 kilometers per second. That's a lot of fuel, but it's manageable. Double the delta V to 6 kilometers per second, and the mass ratio jumps to 7.4. Triple it to 9 kilometers per second, and the ratio is about 20. You're now 95% fuel by mass. At 12 kilometers per second, the ratio soars to 55. At this point, your rocket is essentially a thin metal shell floating on a lake of fuel, with almost no room for the payload you actually want to deliver. Engineers call this the tyranny of the rocket equation, and calling it tyranny is not an exaggeration. It dominates every design, every decision, every rocket ever built. Think of it like this. Imagine taking a road trip across a desert with no gas stations. You have to carry all your fuel with you. Fine, but fuel is heavy. Carrying more fuel means the engine works harder, which burns more fuel, which means you need even more fuel just to carry the fuel you already have. Eventually, adding another gallon barely increases your range because most of it is being used to carry itself. That's exactly what rockets face, but it's worse. A car only has to fight friction and gravity, but a rocket has to throw mass overboard at immense speed to move forward. Every second, it gets lighter, which is good, but it starts absurdly heavy. Take the Saturn V, the rocket that took us to the moon. At launch, it was roughly 85% fuel by mass. Think about that. It weighed about 6.5 million pounds sitting on the pad, and the part that actually carried humans, the tiny command module, was less than 1% of the total weight. The rest? Fuel, tanks, engines, all staged and discarded along the way to shed dead weight. Its design wasn't elegant, it was desperate, dictated entirely by the rocket equation. And yet, it worked. Now let's look at why the moon mission worked, and why Mars is an entirely different beast. To reach low Earth orbit from the surface, you need a delta V of about 9.5 kilometers per second. That's the hardest part of any space mission. You're punching through the atmosphere, fighting gravity every step of the way, and you need tremendous speed just to escape Earth's pull. Once you're in low Earth orbit, the additional delta V required to reach the moon and return is roughly another 6 kilometers per second. But clever engineering made it possible. The lunar module was extremely light, designed only to operate in the moon's weak gravity, which is 1/16 of Earth's. The moon has no atmosphere, so there was no need for heat shields during landing. Its escape velocity is just 2.4 kilometers per second, so leaving the surface required relatively little fuel. The bottom half of the lunar module was left behind on the moon, and only the ascent stage, the small cabin carrying 2 astronauts, had to rendezvous with the command module in orbit. Every kilogram mattered. Every single choice was about saving mass, and it worked. Barely, in some cases, but it worked. The entire delta V budget for an Apollo mission from Earth's surface to the moon and back was roughly 15 to 16 kilometers per second. That's a massive number. The Saturn V was the most powerful rocket ever flown, and it could just barely pull it off. Now, Mars. The first thing you need to grasp is how far away Mars actually is. The moon is about 3 days away. Light your engine, coast for a few days, and you're there. If something goes wrong, you can turn around, like Apollo 13 proved. Mars, on the other hand, is a completely different story. At its closest, it's about 55 million kilometers from Earth. At its farthest, roughly 400 million kilometers. You can't just point your rocket and go, because both Mars and Earth are moving, orbiting the sun at different speeds and distances. You have to launch at just the right time, follow a curved path called a Hohmann transfer orbit, and arrive about 8 or 9 months later. 8 or 9 months hurtling through deep space with no possibility of turning back. Let that sink in. On the ISS, if something goes wrong, you can climb into a Soyuz capsule and be home in hours. On the way to Mars, if anything fails, you are alone inside a metal tube, hurtling tens of thousands of kilometers per hour through the void. There is no abort, no emergency landing. Your only option is to fix it yourself or die. And that's just the journey. The delta V requirements hit hard too. From low Earth orbit to a transfer orbit to Mars, you need about 3.6 kilometers per second. Then, when you reach Mars, you need another 1 to 2 kilometers per second just to slow down into orbit. Then comes the landing, and this is where Mars starts showing its teeth. You might think Mars having an atmosphere is good news. You could use parachutes and heat shields to slow down. But Mars's atmosphere is a cruel middle ground, not non-existent like the moon, but far too thin to fully help. At the surface, it's about 1% the density of Earth's atmosphere at sea level. That's like standing at 35 kilometers above Earth, more than 3 times higher than commercial planes fly. The air is too thin to fully slow a spacecraft, but thick enough to generate extreme heat when you enter at supersonic speeds. You need a heat shield, precise thermal management, and then a parachute. And the parachute can only slow you to about 200 miles per hour, not gentle at all, still dangerously fast. At that point, you must fire rockets for final braking. This is manageable for small robots. Viking landers weighed under a ton and successfully used a combination of heat shields, parachutes, and rockets to land safely. But a human mission? You're talking about 20 to 40 metric tons of crew, habitats, life support, food, equipment, and possibly fuel for the return trip. That parachute trick doesn't scale. To slow such a massive payload, a parachute would need to be hundreds of meters wide beyond anything we know how to deploy at supersonic speed. For humans, rockets must handle most of the deceleration, and every kilogram of fuel you bring to land must be carried from Earth. Remember the tyranny of the rocket equation? NASA estimates that for an all-propulsive landing on Mars, every 1 metric ton you want on the surface requires about 20 tons in low Earth orbit. That ratio alone is enough to give anyone nightmares, and that's just the first problem getting to Mars. Suppose, somehow, you succeed. You land a crew safely with their habitat and supplies. Now they want to come home, and this is where things get even harsher. Mars's gravity is only 38% of Earth's, and the escape velocity is lower, so in theory, leaving should be easier. But you're not on Earth anymore. There's no Kennedy Space Center, no assembly buildings, no team of engineers, no factory, no fuel supply. You're on a barren, frozen world 55 million kilometers from the nearest help, and you must launch a rocket with everything needed to get home. Remember the Saturn V? Thousands of people, billions of dollars, massive infrastructure just to launch one vehicle. On Mars, you have none of that. If you bring your return fuel from Earth, you must land it safely, store it for months or years, and then trust it to launch perfectly. Every kilogram of fuel multiplies across the rocket equation. You need fuel to carry the fuel, fuel to land the fuel, fuel to launch the fuel from Earth. The mass multiplies exponentially. Let's break down the numbers to make it even clearer. To get a crew off the surface of Mars and into low Mars orbit, you need a delta V of roughly 4.1 kilometers per second. That accounts for gravity losses and a small margin. From there, getting onto a transfer orbit back to Earth requires another 2.3 kilometers per second. So just escaping Mars and heading home costs about 6 to 7 kilometers per second of delta V. With a decent rocket engine, say a specific impulse of 450 seconds, your rocket at launch from Mars needs to be roughly 80% fuel by mass. That's 80% fuel on a planet where there is no fuel, and it gets worse. This calculation doesn't even include the heat shield for re-entry to Earth, life support for the journey, food, water, structural mass, or any margin for error. Once you factor all that in, the ratio of fuel to payload becomes obscene. To put this in perspective, consider the Apollo mission to the Moon. The total delta V for a round trip was about 15 to 16 kilometers per second. For a Mars mission, including launch from Earth, transit to Mars, landing, launch from Mars, transit back, and Earth re-entry, the total delta V is in the neighborhood of 18 to 22 kilometers per second, depending on mission design. That might not sound like a huge difference, only a few extra kilometers per second, but the rocket equation doesn't care about intuition. A small increase in delta V when you're already at the limits of what's possible causes an exponential increase in required fuel. You're not just adding fuel, you're multiplying it. The Saturn V weighed about 3,000 metric tons at launch for the Moon mission. A Mars mission using the same propulsion technology, bringing all the return fuel from Earth, might require a spacecraft weighing tens of thousands of metric tons assembled in orbit. That's a scale of engineering no one has ever attempted. And we haven't even touched the cruelest constraint yet, orbital mechanics. The planets don't wait for you. Earth and Mars orbit the Sun at different speeds and distances. Earth takes 365 days to orbit. Mars takes 687 days. Favorable alignment for transfer happens roughly every 26 months. That means you can only launch efficiently at very specific windows. You can't just decide to leave Mars whenever you feel like it. You have to wait for the next launch window. Depending on the mission plan, this could mean sitting on Mars anywhere from 30 days to 500 days, waiting for Earth and Mars to line up again. The most efficient mission profile is called a conjunction-class mission. You fly to Mars in about 9 months, stay on the surface for roughly 500 days, and then fly home in another 9 months. The long stay isn't a choice, it's dictated by orbital mechanics. If you try to shorten it, the fuel required skyrockets because you're fighting the natural rhythm of the planet's orbits. Even a short surface stay of 30 to 90 days requires much more energetic trajectories, sometimes spending over a year just getting home, and the total delta V shoots through the roof. While on Mars, for roughly a year and a half, the crew faces another serious threat: radiation. Mars has no protective magnetosphere and a very thin atmosphere, only 1% the density of Earth's. Cosmic rays and high-energy particles constantly bombard the surface. These particles aren't like sunburn. They penetrate walls, the spacecraft hull, and even your body, breaking chemical bonds and damaging DNA. Radiation accumulates over time. On the ISS, astronauts are partially shielded by Earth's magnetic field, but even there, doses are multiple times higher than safe nuclear worker limits. On Mars, exposure over a 3-year mission could reach about 1 sievert, significantly increasing lifetime cancer risk. Fully shielding a habitat from galactic cosmic rays would require meters of solid material, an impossible mass to transport. The crew would also have to be entirely self-sufficient. The nearest resupply is 9 months away, and you can only send it when the next launch window opens. If something breaks at the wrong time, no one can help for months or even over a year. If a crew member gets seriously ill, there's no hospital, no medevac helicopter, no Earth-based rescue. The crew's own training and supplies are all they have. Psychologically, a team of 4 to 6 people confined in a habitat roughly the size of a couple of shipping containers, isolated from all other humans, with communications delayed by minutes, must cope with extreme stress. Antarctic crews, submariners, and ISS astronauts give us insight into isolation, but those missions last months, not years, and always carry the knowledge that rescue is theoretically possible. On Mars, it is not. And now, back to the fuel problem, because this is where it really hits home. Imagine designing a Mars return vehicle for 4 crew members, with life support for the journey, a heat shield for Earth re-entry, and a structural dry mass of around 10 metric tons. That's optimistic, but let's be generous. To achieve a delta V of about 6.5 kilometers per second with a specific impulse of 450 seconds, the mass ratio required is roughly 4.5. That means a fully fueled vehicle would weigh about 45 metric tons, 35 metric tons of fuel on Mars, where there is no fuel. Every single kilogram of that fuel had to be launched from Earth, survive a 9-month cruise, land safely on Mars, and remain usable for over a year. Then it must work perfectly when the engine is ignited. The chain of mass multiplies at every step. Fuel to carry the fuel, fuel to land the fuel, fuel to launch the fuel from Earth. By the time you trace it all back to the launch pad on Earth, the total mass is staggering, enormous, bordering on impossible with today's technology. Because of this fuel problem, some of the brightest minds in space exploration have proposed a radically different approach. Why not make fuel on Mars itself? This concept is called in situ resource utilization, or ISRU. The idea is simple in theory. Instead of carrying all the fuel from Earth, you bring a chemical processing plant to Mars and use local resources to produce rocket fuel. Mars's atmosphere is roughly 95% carbon dioxide. If you can extract that CO2 and split it into carbon and oxygen, you've got your oxidizer. Add in water ice, which we believe exists just below the surface in several locations, and you can electrolyze it into hydrogen and oxygen. Combine the hydrogen with carbon, and you can produce methane. Methane and oxygen are a rocket propellant combination that actually works and is compatible with engines designed to burn them. On paper, this is brilliant. Instead of shipping 35 metric tons of fuel from Earth and risking every step, you send a processing plant weighing perhaps 1 or 2 metric tons and let it slowly fill your tanks over the course of a year or so. You break the chain that makes the rocket equation so unforgiving. The exponential multiplier of mass disappears, and suddenly the numbers look much more achievable. But, and there is always a but in engineering, making fuel on Mars is something we have never done. Not once. No demonstration at meaningful scale. Our robotic explorers have achieved remarkable feats of science, but none have ever taken the Martian atmosphere or ice and chemically processed it into usable rocket fuel in significant quantities. The chemistry itself is understood in the lab. Take CO2 from the atmosphere, apply energy, split it into carbon monoxide and oxygen, or take water ice, electrolyze it into hydrogen and oxygen, and combine hydrogen with carbon to make methane. Methane and oxygen burn well in rocket engines, but knowing the chemistry and executing it at scale on another planet are 2 completely different challenges. Scaling a laboratory demonstration up to 35 metric tons of fuel on Mars requires multiplying operations by millions. It's not just a technical problem, it's an entirely new level of engineering complexity. And even if the chemistry works perfectly, the environment of Mars adds layers of difficulty. Temperatures swing from hundreds of degrees below zero at night to relatively mild during the day. Dust storms can envelop the planet for weeks, blocking sunlight needed for solar-powered chemical processing. Equipment must operate autonomously for months or years without repair. Any failure means the fuel supply might never reach usable levels, stranding the crew with no way home. This is not a theoretical concern. It's the reality of working in a place where nothing exists to support human life except what you bring or create. Once the fuel is made and stored, it has to survive without degrading, boil off, or leaking for the entire duration of the crew's stay. When the time comes to launch, the rocket must ignite flawlessly. One misstep, one damaged tank, one stuck valve, and the mission could fail entirely. All the same exponential multipliers from the rocket equation come into play. Fuel must be carried to land, fuel must survive on Mars, and fuel must launch the crew home. The margin for error is microscopic. This is why human missions to Mars are orders of magnitude more complicated than the moon landings. The moon was a technical marvel, but Mars is a logistical, engineering, and environmental nightmare combined into one. And there's more. Even if the fuel problem is solved, the crew still faces the psychological and physical challenges of isolation. They'll live in habitats no larger than a couple of shipping containers with a tiny team of 4 to 6 people, completely cut off from Earth for months or years at a time. Communication delays range from 10 to over 20 minutes, so real-time guidance from mission control is impossible. If a critical system fails, the crew must repair it themselves. If someone falls seriously ill, there's no hospital, no evacuation. Their only resources are their own training, whatever medical supplies they brought, and hope. The isolation alone can degrade performance, strain relationships, and cloud judgment. On Earth, even in extreme isolation, there's at least a theoretical chance of rescue. On Mars, there is none. Radiation adds another brutal layer of risk. Mars has no magnetic field, and the atmosphere is far too thin to shield the crew. Cosmic rays and high-energy particles constantly bombard the surface, penetrating walls, equipment, and human tissue. The damage accumulates over time, breaking chemical bonds, damaging DNA, and increasing the long-term risk of cancer. Over a 3-year mission, the total exposure could reach about 1 sievert orders of magnitude higher than safe occupational limits. The crew must rely entirely on shielding in their habitat and spacecraft, which adds weight and complexity. Every kilogram of mass dedicated to radiation protection is a kilogram that cannot be spent on fuel, life support, or supplies, further complicating the mission. Now let's bring everything together and really feel the weight of this problem. Imagine designing the Mars return vehicle. It has to carry 4 crew members, life support for the journey home, let's say around 200 days, a heat shield for re-entry, and structural mass, which includes everything except fuel, around 10 metric tons. That's already optimistic. To achieve a delta V of roughly 6.5 kilometers per second with a specific impulse of 450 seconds, the required mass ratio is about 4.5. That means a fully fueled vehicle would weigh around 45 metric tons, 10 metric tons of payload, and 35 metric tons of fuel. 35 metric tons of rocket fuel on Mars, where there is no fuel, and the nearest gas station is 55 million kilometers away. Every single kilogram of that fuel had to be launched from Earth, survive a 9-month cruise, land safely on Mars, and remain usable for the crew's entire stay. Then it must ignite flawlessly to return the crew home. Every step multiplies the mass requirement. Fuel to carry the fuel, fuel to land the fuel, fuel to launch the fuel from Earth. By the time you trace it all the way back to the launch pad, the total mass is staggering. It's not just expensive, not just difficult, it approaches the limits of what is physically possible with current technology. This is why ISRU, making fuel on Mars, is such an attractive solution. Instead of bringing 35 tons of fuel, you send a processing plant weighing 1 or 2 tons and let it work for a year, creating the fuel locally. That breaks the exponential chain imposed by the rocket equation, turning an almost impossible mission into a feasible one, at least on paper. But feasibility on paper is very different from feasibility in reality. We have never done this before, not even a small-scale demonstration of producing rocket fuel on another planet. Our robotic explorers have done incredible science, but none have chemically converted Martian CO2 or ice into usable rocket propellant at meaningful quantities. The chemistry is understood, but scaling it up to tens of tons of fuel on a harsh, frozen, dusty planet with massive temperature swings, autonomous equipment, and no margin for error, that is something humanity has never attempted. And until we do, sending humans to Mars safely remains more than just a technical challenge. It's a monumental logistical and engineering puzzle. Combine that with the environmental and human factors, radiation exposure, isolation, psychological strain, life support, delayed communications, and the impossibility of immediate rescue. Every system, every process, every kilogram of mass must be planned, tested, and executed perfectly. There is no backup plan, no halfway solutions, no quick fixes. Mars is not a bigger moon. It is a fundamentally different problem, one that challenges physics, engineering, human endurance, and ingenuity simultaneously. The moon missions were a triumph, yes, but they give a misleading sense of scale. They make Mars look like just a longer trip. In reality, Mars is exponential, unforgiving, and every small miscalculation multiplies into enormous consequences. So the next time someone casually says, "We went to the moon, so Mars is next," remember this: it's not just farther, it's an entirely different universe of challenges.